Hello and welcome again to our Target JEE Advanced video series. Today we are going to talk about the chapter of alternating current, AC, right? Now, the way we are going to go about this video is first I'll do a quick analysis of this chapter, right? About the questions that appeared in the previous year's papers of JEE Advanced and JEE Mains. And then we'll do a quick summary of this chapter. Very quickly we'll go through what we call as a rapid revision. And then of course we'll have some fun with the questions of this chapter. Now, while watching this video, if you genuinely feel that you have learned something and if we were able to help you in some way, then please do subscribe to our channel and hit the bell icon. So with that, let's start with the analysis of this chapter, right? If I talk about JEE Advanced, then in year of 2018, we had just one question from this chapter, which was based on an LR circuit. That's an inductor resistor circuit, right? In 2017, there were 3 questions from this chapter, right? One of them was from LCR circuit, one of them was just from LR circuit, and one of them was to find VRMS. Now, in 2016, there were no questions, 2015, there were no questions, and in 2014, there was just one question from an RC circuit. Now, if I talk about JEE Mains, then in 2018, there were 2 questions, which was from quality factor and from power, which was new. Quality factor is not usually asked. In 2017, there were no questions. In 16, there was just one question from LR circuit. In 15, there were 2 questions from LR circuit and LCR circuit. And again, in 14, there was just one question from LR circuit. So, you see that the crux of this chapter is around this one idea of LCR circuit, okay? And a little bit of resonance and here and there. So, most of the questions are just asked from that concept. So, the way I look at this chapter is that, if you know how to deal with an LCR circuit, then you pretty much know the entire chapter, right? That's the crux is there in your hands. So with that, let's start the summary for this chapter. This chapter is called alternating current. It means it's about current that alters. It's about current that changes, right? So in this chapter, we have a current which varies sinusoidally. So this is the way it varies, right? Like a sine curve. And the equation for this current, or the expression for this current, is I equals to I naught sine omega t plus phi. So the first thing we learn here is what are these things? What is I naught? So I naught is called the peak current, right? That's the maximum current which is possible in this kind of graph, which is this value here. This is I naught. This you can say is minus I naught, right? Now the next thing is, what is omega t plus phi? What is this thing inside your sine? That is called the phase of the current. That entire thing is called the phase at any time t, right? And in this phi particularly, which is added to the omega t, is called the initial phase. This was the phase which the current had in the beginning, right? Here in the diagram which I have drawn, the initial phase is 0 because it is, at time t is equal to 0, it is starting from 0 itself. So phi is 0 in this particular case, but phi in general means the initial phase, right? Then you have omega here. The omega is called the angular frequency, right? Angular frequency, time period, and your regular frequency or the linear frequency, these things are related to each other, right? Time period is basically the time it takes to cover one full circle, right? So from here the current would start, it will go like this and come back here. This whole thing will be one circle, one cycle, right? So the time it takes to cover that one cycle is your time period, right? You take 1 by time period, that gives you the frequency, that is the number of cycles you are having in 1 second. And then when you multiply it with 2 pi, you get omega, which is called the angular frequency. So we have all these things sorted, right? Then if you have an alternating current in a circuit, it means that the EMF in that circuit, right, the voltage in that circuit is also alternating. A direct voltage cannot give you an alternating current, right? So your EMF is also alternating, and EMF is E naught sine omega t plus phi dash. So you see that the initial phase here and initial phase here need not be same all the time, right? The next thing we see is the average current which is drawn to the circuit in one full cycle, right? To find that, what we do is, let's say this is what we're talking about. This is one full cycle from here to here, right? If I want to find the average current, what I have to do is I have to find the area under the current time graph, which is basically this area, then divided by the total time, right? So the area under the current time graph, if you have learned area under curves, is that is the integration of I as a function of time dt, integration of that from whatever your t1 and t2 is. In this case it is 0 to t, right, divided by the time difference. So t2 minus t1 in this case will be t. Now if you want to find the average current which your battery delivers in a full cycle, right, that comes out to be a good 0. And that makes sense, right? Because when it begins moving in one direction. It achieves the maximum in one direction and goes down to zero in the same direction, and it starts moving in the opposite direction. The same thing happens. So you find as an average what has happened? Nothing. Like if you say after full cycle how much average current went through the circuit, you would say nothing, because half the time it was in one direction and other half it was in the opposite direction with the same increase and decrease. But the interesting thing here, or the interesting quantity here, is not the average current, because it's zero. It is the RMS current. Now RMS current is called root mean square current, and that's a fancy current, like a root mean square. What does that mean? It means that you take the root of something. That's why the word root comes first. So this is the root, right, of the mean of the square. So you take the mean, that is integration of T1 to T2 by T1 by T2. You know how to find the mean of the square of the current. So while finding the average, you are finding the mean of just the current. Now you're finding the mean of the square of the current. So this is the root mean square current. Now you might be wondering, why in the world would I want to do that? Why would I want to find the root of the mean of the square? Why would I want to do that? So interesting thing is, when you find that the RMS value for one full cycle, you get it to be equal to I0 by root 2. I0 was the peak value divided by root 2, right? Now what is really interesting about this RMS current is, let's say you have a resistance, okay, and there's an alternating current flowing through it, and in one time period you find that the heat it generates is some H, okay. Now I want to generate the same heat H using a direct current. Then what amount of current should I use? Should I use I0 amount of current, which is the peak, which in my AC case, or should I use like I0 by 2? Should I use I0 by 3? Because in DC, the current is going to be fixed. What is that fixed value of current that I should use so as to generate the same power, the same heat in my resistance given the same time? So it turns out that value is IRMS. So IRMS is very IRMS relates an AC circuit to a DC circuit in terms of power. Okay, they produce the same power for the same time. So IRMS is really important. It is I0 by root 2. Don't forget that. Now we have to see how to deal with circuits with an AC source, right? Here I have a circuit with a resistor and an AC source. Now in this particular circuit, this one is really simple. Here the current is I is equal to I0 sin omega t plus phi, and E is also E0 sin omega t plus phi. So in this case, I and V, that is the current and voltage, are in phase. Okay, they don't lag or lead. They both move in phase. Now if I want to represent that, I can represent that in something called as a phasor diagram. So here I have a phasor diagram in front of me, right? I have drawn this phasor diagram to see what is the relationship between I and E. You can draw phasor diagrams for different purposes. So this one is for I and E. So I can see that I, or I0 here, is in the same direction as your E0. Okay. Now in this kind of phasor diagram where you represent I and E, because the actual value of current and the actual value of EMF is going to change with time, right? So these two things, they move on this plane anti-clockwise, but they will move in such a way that both of them are together all the time. I0 and E0 are together and they move like this, okay, depending on whatever the time is and whatever the phase is at that particular time. All right. Now this is simple. If you want to find the power, in this case it is just VRMS times IRMS, as I told you that RMS is relates to the power, and you'll get the average power for one full circle. In one full cycle, how much power is delivered. Okay. Now let's look at other kinds of circuits. The next thing that we see is a purely inductive circuit. So now this is a circuit in which you just have an inductor and an EMF source, an AC source, right? Now in this kind of circuit, there is still some hindrance provided to the current, and that hindrance is called inductive reactance, okay, XL, which is given by omega times L, where L is the inductance of that inductor. All right. In this kind of circuits, the voltage leads the current by a phase of pi by 2. Okay. Remember that in a resistive circuit, the voltage and current, they both were in phase. Here the voltage leads current by a phase of pi by 2. Now when I have to draw the phasor diagram, right, the way I draw it is, I have got my voltage over here, which is E0, right, the peak voltage, and the current over here, which is I0, right. So here we say that the voltage is leading current, because I know that the phasor moves anti-clockwise like that, right. So when it moves anti-clockwise that way, the angle between this E0 and I0, that is the phase between both of them, would always remain this 90 degrees. So when they turn like this, right? So this is a very important thing to remember. In a purely inductive circuit, voltage leads current by a phase of pi by 2. Now in this case, if you want to find the IRMS, the current, the root mean square current, then that will be equal to the ERMS divided by XL, okay? And the average power delivered to the circuit in a full cycle, in this particular case, is equal to 0. Now we deal with purely capacitive circuit. In a purely capacitive circuit, all you have in a circuit is just a capacitor and an AC source, right? There's no resistance at all. In this case also, there's some hindrance provided to the current, and that is called the capacitive reactance, which is 1 by omega C. Remember, the inductive reactance was omega L, but capacitive reactance is 1 by omega C, okay? Now in this case, the current leads voltage by a phase of pi by 2. In our inductive circuit, voltage led current. In this particular circuit, the current would lead voltage, right? The way I remember it is like C for capacitance and C for current. So capacitance sort of favors current. That's the mnemonic that I have, right? So current leads voltage by pi by 2. In this case, if I have to draw the phasor diagram again, here you see I0 would lead the E0, okay, and by an angle of pi by 2. So when they rotate anti-clockwise, you'd see that the angle between them is always maintained, okay? So that's how the phasor of this particular setup looks like. Now if you want to talk about the power delivered in the circuit in one complete cycle, that is again equal to 0. So average power delivered is 0 in a pure capacitive circuit as well. Next we have in front of us our LCR circuit. Now this is a really important part, right? Here we have got an R, a resistor, we have got an L, the inductor, and the C, that is capacitor. Now in this kind of circuit, there is both inductive reactance, which is omega L, and capacitive reactance, which is 1 by omega C, as well as the resistance of the resistor, which is just R. Now in this kind of circuit also, we can define the net hindrance, or the net opposition to the current, which is called impedance. Now impedance is found out by this formula, which is root of R square plus XL minus XC the whole square. All right. Now that's fine, but now the question is, what is basically happening in this particular situation? Is the current leading the voltage or voltage leading the current? What is actually going on, right? And what is the actual phase with which the current would lead voltage or voltage would lead current? I don't know that, because I know in inductive circuit, voltage led current by pi by 2, and in capacitive, the reverse happened, but the phase was still pi by 2. But here that might not be the case, right? It would depend on how powerful your inductor or how powerful your capacitor is. And to figure that out, right, we draw another kind of phasor diagram. You can call it the impedance phasor diagram or the reactance phasor diagram or whatever. So this is not a phasor diagram between I and V. This is a phasor diagram between the reactance of L and C and the resistance, okay? So we represent the resistance on the x-axis like this, my R. Then on the positive y-axis, we represent the inductive reactance, right, which is omega L. And on the negative y-axis, we represent the capacitive reactance, which is 1 by omega C, right? Now, depending on whether omega L is greater than 1 by omega C or 1 by omega C is greater than omega L, that is, whether the inductor is more powerful than the capacitor or capacitor is more powerful than the inductor, that kind of sort of gives us what would be the phase with which the current would lead voltage or voltage would lead current. So let's look into that. So here I have taken a special case where I'm saying that, okay, fine, let's consider that XL is greater than XC. That is omega L is greater than 1 by omega C. Now you see XL is over here and XC is over here, right? If I say XL is more than XC, it means that the net resultant of these two would come on the upper side, right? On the positive Y side, like this here, right? It means that inductor has an advantage over here in this circuit than the capacitor, right? And the net reactance of them together is omega L minus 1 by omega C. And here is your R, right? When you find the resultant of these two values, that is of omega L minus 1 by omega C, which is this, and the R here, you get a vector like this, or what we call it as a phasor like that, okay? And the phasor makes an angle with the x-axis. That angle is your phase, basically the phase difference between the current and the voltage, right? This is the phase with which either the current is leading or voltage is leading. In this particular case, because this particular circuit favors the inductor, because XL is more than XC, it means that voltage leads current by a phase of phi, okay? If it were the opposite case, where 1 by omega C was more than omega L, then in that case, if you drew this, you'd get this, here is where you'd get the net, and this is where your R is. So when you find the resultant, you'll get something like this, right? So in that particular case, what happens? This is your phase, right? That will be your phi, and that in that case you'll say that because the circuit favors the capacitor, the current leads the voltage by this phase of phi. All right. So that's how you look at a LCR circuit. You have to find out what is the tendency of the circuit, whether it is towards C, whether it is towards L. It can also be so that, you know, omega L is actually equal to 1 by omega C, in which case it favors none, and the phase difference between the current and voltage would be 0. Now in this case also we can find power. Power is given by Vrms times Irms times cos phi. So you have an extra factor of cos phi coming into here in this, and this cos phi is called the power factor. Otherwise the power would have been just Vrms times Irms, right? But in this case there's an extra cos phi which is multiplied to it, so that's called the power factor. All right, let's move ahead. Now let's talk about the special case in which omega L becomes exactly equal to 1 by omega C. Now when that happens, you see, right, in our phasor, this omega L is equal to omega C means this net is 0. So all you have is that resistance, right? It means that the impedance, you remember, impedance was equal to root over R square plus XL minus XC whole square. That was your impedance, right? Now this impedance, this value is 0. So impedance becomes equal to R, which is actually represented by Z, not X, right? So Z becomes equal to R. What does that mean? It means that if XL becomes equal to XC, right, there's a factor in impedance which will become 0. So if XL was more than XC, still there will be some factor which will add to this. If XC was more than XL, even then there will be a factor which adds to this because there's a square which is getting added. But if XL becomes equal to XC, it means that there is no extra resistance of sort which is getting added to the resistance of the resistor, right? There's no hindrance provided by the combination of capacitor and the inductor. What does that mean? It means that in that particular situation the current would peak. That would be the maximum current in the circuit when that particular situation occurs, right? And that particular condition is called the condition of resonance, right? When omega naught L, because omega naught is what we call as the resonant frequency, becomes equal to 1 by omega naught C. So we find that omega naught is equal to 1 by root over LC. So if you have an LCR circuit, you find 1 upon root over LC, you know that at this particular frequency the current will be maximum. This fact is used to in radio transmission and all that. When you tune into a particular frequency, what you're basically doing is that for that particular station, that is the resonant frequency. When you tune into that particular station responds to that, because you can say the signal being sent by that station peaks at that particular frequency. The same thing is also used in your SIM cards. All right. So the next thing that we need to learn is called the quality factor. That kind of tells us how sharp the peak of this resonant frequency is, because you see current peaks. If I draw current versus frequency, current peaks at a frequency which we call as the resonant frequency. This is a very famous diagram, by the way, you can see in your books and all. So the quality factor basically tells you how sharp that peak is, which is given by the voltage across L or C, right? You can take either of one of them at resonance. They're going to be same, right? Because you know what is voltage? Voltage is basically I times of R, and R for both of them, or the impedance for both of them, is same, I times of X, you can say, right? And I will be a constant current, like a particular current flowing through that circuit. You can take IRMS also, divided by the applied voltage, right, which is also a fixed number. So you get the quality factor equal to 1 by R times root over L by C. You have to remember this. If you remember that won't be the worst thing in the world. 1 by R times root over L by C. So one of the question was recently asked from this particular topic, okay? Now the next thing which we see is the last topic of this chapter, which is called transformers. Now what happens is, so when you have like really long cables between which you want to supply power, right? We found out that when you have very high current in those cables, what happens is that there's a lot of loss of power happens because of heating. So we wanted to create a system in which we can reduce current but still not compromise with power, okay? So we came up with the idea of a transformer. Now a transformer is one which has like a lot of coils on one end and a few coils on the other end. The number of turns is different on both ends. Let's say here, this is called the primary, by the way, this is called the secondary. So let's say the number of turns in primary is NP and the number of turns in secondary is NS, right? Then because of this and because of this soft core iron that you have in between, and I'm not going into the detail of how because changing of the flux sort of creates the EMF in the other end of the wire, and all that there is there in the theory. So in the summary, I'm not going into detail of that. What I'm going to tell you is how the ratio of the voltages come out to be. So the ratio of the voltage of primary by secondary. So if the primary is at a voltage of EP and secondary is at a voltage of ES, the ratio is equal to the ratio of the number of turns. That is NP by NS. Okay. So if let's say your primary has 1,000 turns and the secondary has like a 20 turns, right? So it will be 1,000 by 20. That will be like what, 50. So your power would get stepped up, we say, by a factor of 50. Okay, and it is inversely proportional to the current. Okay, so NP by NS is equal to EP by ES is equal to IS by IP. So in this particular setup, what happens, the ratio of the EMF at the primary to that of the secondary is equal to the ratio of turns at the primary to that of the secondary. Okay, so EP by ES is equal to NP by NS. That's very important to remember. Now I had told you that the power remains same, and that was the objective with which we had made this transformer, right? So power at the power delivered at the primary is equal to the power delivered at the secondary. What is the power delivered at the primary, by the way? It will be EP, which is the EMF of the primary, times IP. This should be equal to ES times IS, and this is a condition which remains true. So you can see that EP by ES is equal to IS by IP. Okay, so I can say that this is equal to IS by IP. Alright, so this is something you have to remember, that EP by ES is equal to NP by NS, which is equal to the ulta, which is IS by IP for a transformer. And here this NP by NS ratio is called as the transformation ratio. This problem says that at steady state, a current of 4 amperes is in a coil which is connected to a 12 volt DC source. And if the same coil is connected to a 12 volt 50 radians per second of AC source, a current of 2.4 amperes flows in the circuit. What is the inductance of the coil? Okay, so there is a coil which has some inductance and it is first connected to DC and then AC. Okay, then it says what would be the power developed in the circuit if you connect a 2500 microfarad capacitor to it in series with the coil. Okay, so now initially the circuit had just a DC supply, then it got an AC supply, and then it also got a capacitor added to it. Alright, so there are basically 3 situations here, right? Let's look at the first situation, right? You have a coil and you have a DC source there. The coil would also have some resistance, right? So I'm going to represent the resistance of the coil like this, like R here, okay? And this is the inductance of the coil, L. Now, what can I get from here? Now, it says that at steady state, the current is 4 amperes. What does that mean? It means that the inductor is not providing any opposition to the current. That's what steady state means, right? Now, if I have to find, so basically this inductor, it is as if like it is just short circuited. It's not doing any opposition to the current, although the resistance of the coil is making some difference. And I know that the EMF is 12 and the current is 4. I can find out this resistance. The resistance will be equal to 12 by 4, which is equal to 3 ohms. Okay, so the resistance of the circuit is 3 ohms. In the second situation, what happens? We connect this to an AC source, and when you connect an inductor to an AC source, right, the opposition and everything would come into the picture, and you can't just, there's no steady state or as such, right? Now here I know that this is 3 ohms. I just calculated, and there must be some inductive reactance of this inductor which I don't know. I know that the current flowing is 2.4 amperes and the EMF is 12 volts. Alright, what can I do to find the XL? Well, I know the current, I know the EMF, and whenever in a problem you just stated the current, it means that you're given the RMS current. So 2.4 is RMS current and 12 volt is RMS EMF. Okay, now I can find the impedance of the circuit. The impedance of the circuit will be VRMS divided by IRMS, right? What is VRMS? 12 by RMS is 2.4. What is 12 by 2.4 is 5, right? So the impedance of the circuit is 5 ohms. I calculated that. Cool. So I know the impedance and I know this resistance. There's another way to find impedance, right? Impedance is equal to, or square of impedance is equal to R square plus XL minus XC whole square. This is the formula. In this particular circuit, there is no XC, there is no capacitor, so this term would go 0. So you get, basically, I know this Z, I know the R, XL can be calculated. So Z is 5, so 5 square is equal to 3 square, R is 3, plus XL square. That gives me XL is equal to 25 minus 9 is 16, and the root will be 4, it will be 4 ohms. So I calculated XL to be 4 ohms. Okay. So now I know the inductive reactance of my inductor, and I know the resistance of the resistor as well. Now comes the third situation, where you also connect a capacitor to the circuit, and you are supposed to find out the power developed in the circuit. Now I know this R, I know this XL, I don't know this XC, right? What is XC, by the way? XC is equal to 1 by omega C. See, C is already given to me. Omega is also given, 50 radians per second, right? It's the angular frequency because it's in radians per second. No, I can find the XC, which will be equal to 1 upon 50 radians per second times C is 2500 microfarads. That is 10 to the power of minus 6. When you calculate that, you get it to be equal to 8 ohms. Alright, so you have found the XC as well. So now you know R, you know XL, and you know XC. Now we have to find power in this circuit, right? Power is Vrms times Irms times cos phi. Now in this particular circuit, I know what the Vrms is, it's 12 volts. I don't know the Irms, but I can find out because I know everything. I can find the impedance and find Irms, not a big deal. But I also need cos phi, the power factor, right? For that I'll have to draw the phasor diagram. Let's do that. So let's quickly draw that. Here on the top we have the XL, here we have XC, here we have R. So R is equal to 3, so this is my 3 here. XL is equal to 4, so this is 4 here. And XC is equal to 8, so this here is 8, right? Alright, so 3, 4 and 8. So the net is going to be towards the capacitor side, which will be 4. So I'll get a 4 here, right? Okay, so now this is 4, this is 3. The resultant of that will be 5, right? Over here like this. This is your 5. Forgive my bad diagrams. This is 5, right? Right. This is 4. This is 3. This is 5. And what this angle would be? I can find that angle, right? Because I know this triangle. I know the length in this triangle. I can find that angle very well. Basically, I need the cos phi. So cos phi can be found out. Cos phi will be equal to this, which is equal to 3, right, divided by this, which is equal to 5. So 3 by 5 is my cos phi. So one part of the power, right, power average, which is equal to Vrms times Irms times cos phi. Cos phi we have calculated. Now let's find out the other thing, which is Irms. So alright, what I can do is I can represent this thing because I know Irms is equal to Vrms by R. So I can say this is Vrms squared by, not R, Z, right, the impedance times cos phi. So I have to find the impedance of this entire circuit. So what will that be? I know that Z is equal to, or Z square is equal to R square plus XL minus XC the whole square. So in this case, Z square will be equal to 3 square plus XL, which is equal to 4. So it will be 4 minus XC, which is 8 whole square. So that will become how much? That will be Z square equal to 9 plus 16, right? It will be 4 square is 16. So Z will become equal to 5. Right, root of 25. So Z is equal to 5. So I can get my average power from this equation that we had found. Let me do it here. Average power equal to Vrms square, which is 12 square, by Z, which is 5, times cos phi, which is 3 by 5. Okay. When you calculate that, you get that to be equal to 17.28 watt. Okay. And that is the right answer. So we are given a circuit in this problem, right? And it is told to us that the XC, that is the capacitive reactance is 100 ohms, the inductive reactance is 200 ohms, the resistance is 100 ohms again. We have to find the effective current through the source. Now, please notice that this is an LCR circuit in which LC and R are not all in series, right? R is not in series with XC and XL. Now, how would I solve this problem? Alright, the first thing I notice is this R, right? I see that the potential difference across this R, right, is not going to change. In the sense that it's going to change, but it's going to be just this AC source which is against this R, right? So I can find the RMS value of current which is passing through this resistor, right, which will be IRMS equal to VRMS by R. Simple. So VRMS is 200, R is given to us as 100, so that comes out to be 2 amperes. So 2 amperes of RMS current would be flowing through this, we can say, right? 2 ampere of RMS current is flowing through this resistor. Well, it's almost like, you know, you can hide this entire part. You can just hide this, and you can just say that, you know, there's a lonely resistor against an AC source. What will be the RMS current? You can find out anytime. But when these guys come into the picture, what are they doing? They will also have some RMS current flowing through them, and that will be determined by the impedance of their branch. What is the impedance of their branch? Okay, so is just XC and XL. So the impedance just will be XC minus XL, because, you know, impedance is equal to square of impedance is R square plus XC minus XL. R here, there's no R in this branch, so it's 0. XL minus XC whole square, and then square would get cancelled, so you just get XL minus XC, actually mod of that. So you simply can get the impedance of that to be equal to XC minus XL. You can take the mod of that, that will become to be 100 ohms. So impedance is 100 ohms. So the RMS current in that branch will be VRMS by the impedance of that branch. So what will that be? VRMS is 200, impedance of that branch we found out to be 100, again is equal to 2 amperes. So the RMS current in this branch is 2 amperes, RMS current in this branch is 2 amperes, so the net RMS current would be just 4 amperes, 2 plus 2. And option number B is your right option, except for that it is not. This is a mistake. Okay, so we know that we use Kirchhoff's junction law very frequently while solving circuits, and when you have a DC source, we know that if a 2 ampere current is flowing this way and 2 ampere current is flowing this way through a junction, the net current should be just 2 plus 2 is equal to 4. That's like kindergarten stuff for us now. But in an AC circuit, things become a bit weird. Now what's happening here, the RMS current here is 2 amperes, the RMS current here is 2 amperes, but these two branches, they are not in phase. Okay, so that means that if the current in the resistance branch is going like this, the current in the other branch, the one that has capacitor and the inductor, might not start from 0, it might start from somewhere here. It's possible. So there's a phase difference. So you cannot add the RMS currents the way you add currents in your DC circuits. Okay, so be very clear about that. So what do? You draw a phasor diagram. So I'm going to draw a phasor diagram here. This is the current in my resistance branch, which is 2 amperes. Now the thing is, I know that the reactance of the inductor is more than the reactance of the capacitor. It means that the inductor capacitor branch is basically behaving like more like an inductor than a capacitor, right? It means that the current would lag voltage there. It means that the current in the resistance branch, the pure resistance branch, would lead the current in the inductor capacitor branch, right? So, and because XL is more than XC, so what would I do here? I would draw the current in that branch below that, because I know that this turns anti-clockwise. Okay, now what will that be? I know that the V is 200 and XL minus XC is again 100, so this is equal to 2 amperes, which I had already calculated, right? So a 2 ampere current is flowing, but with this phase, and there's a 2 ampere current flowing in the resistor with this phase. So what is the net current that is being supplied by the voltage? That you'll have, when you find that, you'll have to find the phasor resultant of these two things. Now this is weird because we're sort of adding currents like we are adding vectors, but actually this is not vector, these are phasors, and we have to do that because there's a phase difference between both of them. This comes out to be, yeah, this is 90 degrees, so this is 2 root 2. So 2 root 2 is the amount of current which the EMF source is supplying to the two branches together in the sense, right? And this kind of seems weird because I want to repeat that, because the RMS current in one of the branches is just 2 amperes and other branch also is 2 ampere, but we cannot directly add them because there's a phase difference. So that is one thing you have to keep in mind while solving problems of AC where things are not in series. In this problem, we are given an RLC circuit which is in series, and there are some voltmeters connected to it. We have said that the voltmeter V1 reads 100 volts and the voltmeter V2 reads 120 volts. And V1 you can see is connected between the resistance and the inductor, and V2 is connected between the inductor and the capacitor. The source voltage is given to you as 130 volts. And we have to mark out the correct statements for this situation. The voltage across resistor, inductor and capacitor are blah blah blah, and the power factor is this, and what is the nature of this circuit. So we have to basically find the voltages across each of these devices, each of this electrical apparatus. Now how would I do that? So I know that the total voltage is 130, and let's say the potential difference across the resistor is some VR, across the inductor is some VL, and across the capacitor is some VC. Can't I just say that V will be equal to VR plus VL plus VC? Can I just say that? Because that's how we do things, right? Like the total potential difference should add up to the potential difference of the battery, because that's providing all the potential differences. And I know the potential VL plus VC is known to me, and VR plus VL is also known to me, so I can somehow, and V is also known to me, so I can find out all of them individually. That's what I thought when I saw the question for the first time, and this is absolutely wrong to do this in an AC circuit, because there's this dangerous thing in an AC circuit called as the phase, and because of the phase you can't write this equation in the first place, because you can't say that. So here we know that the resistance is in the same phase as the EMF, and the phase of VL and VC, the inductor and the capacitor, are 90 degrees out of or in phase, right? All those things there. So what happens is, let's say this is your voltage across your inductor, which is VL, let's say, okay, this is your VC and this is your VR, right? When you find the net, you'd get, I don't know whether VL is more than VC, I don't know that. So let's say that VL is more than VC. So you'll get a final resultant over here, that is VL minus VC, and this is your VR. The net will be what? The net voltage square will be VR square plus VL minus VC whole square. Okay, and this is the V which is given to us. So you see, I cannot write V is equal to VR plus VL plus VC. I can't do that. I have to use this equation. Okay. Similarly, when I'm given that the potential difference between the resistor and the inductor is 100 volts, it doesn't mean that VR plus VL is equal to 100. What it means is, because I know between the resistor and the inductor the phase difference is pi by 2, I can say VR square plus VL square, because there will be in different axes, right, is equal to 100 square. That is what is given to us. Okay, and between an inductor and a capacitor, the phase difference is basically of pi, right? Because this is 90 degrees, the inductor would be 90 degrees ahead of the resistor, and this will be 90 degrees behind. So between them the phase will be 180 degrees. It means that we have to basically directly subtract them. So the difference between them will be VL minus VC, mod of that is equal to 120. Okay, so it's the difference of their potential difference. That is what 120 is, not the addition of their potential differences. Alright, so this is what I have gotten. I know this equation, I know this equation, and this also I can figure out, because see here I know V, so it is 130 square, right, is equal to VR square. What is VR? I don't know what VR is. VR square plus VL minus VC I already know is 120. It is 120 squared. So VR becomes equal to 130 squared minus 120 squared, which is equal to 2500 if I'm not wrong, because 169 minus 144 is 25. Yeah, so VR square becomes this, and VR becomes 50 volts. Okay, so I figured out the potential difference between potential difference across VR, which is 50 volts. Now let's find the other ones. So I can use this equation, right, because I know VR already, so I can say 50 square is plus 50 square plus VL square becomes equals to 100 square. So VL square becomes 100 square minus 50 square, that becomes equal to VL will become 50 root 3 volts. Okay, now that I have found out VL and VR, I can also find VC, right? I can use this equation and I can say that this equation says VL minus VC is equal to 120, or VC is equal to minus 120 plus VL. So that will become minus 120 plus 50 root 3. Okay. So the thing is, I got the value of VC as a negative value, but VC is what it is exactly. It's the RMS voltage across the capacitor, and RMS voltage across a capacitor or an inductor or anything cannot be negative, because that's how we define RMS. It is the peak value divided by root 2. So what's wrong with this? The thing which is wrong is the way I opened this mod, right? I can also say that it is either this or VL minus VC is equal to minus 120, right? You know that when you have mod x is equal to 5, it means that x can be either 5 or it can be minus 5 as well, right? So when I do that, I get the value of VC equal to 120 plus VL, which is equal to 120 plus 50 root 3 volt. So I have gotten the value of VC as well, which is 120 plus 50 root 3 volts. So I found out VL, VR and VC, and I see that option number A is the correct option, the option B is wrong. Now I have to find the power factor of the circuit. How would I find the power factor? So here I have got VL, which is VL will be here 50 root 3. Okay, then I have VC, which will be in the downwards, which is 120 plus 50 root 3, and then I have got R, which is over here, which is 50 volts. Okay, the net of these two is 120 in the downward direction, right? Because this will get subtracted, so you get 120 here, so you have 120 in the downward direction, and this is 50. What would be the resultant of both of them? The resultant of both of them will be 130, which is already given to us in the problem. We have already found that out, right? So basically phase will be the angle between these two guys, this 50 and this 130. So phi, or you can say cos phi, is equal to 50 by 130. Okay, and from there you can say that the power factor, which is basically cos phi, is equal to 5 by 30. Now the thing is, you didn't have to do this actually to find the power factor, because you can directly find power factor by using this formula. Power factor is equal to VR by V, okay, or in general, or you can say R by Z, because you know R is this thing and Z is going to be this resultant. The angle between them, the cos of that angle, is what is going to give you the power factor. So you don't have to draw this to find it. You see that the resultant we already knew, it's 130. We could have directly used that result. Okay, so power factor is equal to 5 by 13. Now we can clearly see that the potential difference across the capacitor is more than that of inductor, so it's a capacitive circuit. So option D is also correct. So option A, C and D are the correct options. In this problem, you are given a series RC combination and it is connected to an AC voltage with an angular frequency of 500 radians per second. Alright, if the impedance of the RC circuit is R times of root 1.25, oh, strange, the time constant of the circuit is, we have to find the time constant of an RC circuit which has an AC source. Okay, what is time constant, by the way? Time constant is simply R times of C. Okay, so when they ask you time constant, don't get freaked out, because all you have to find is the product of the resistance and the capacitance. Okay, that's what it means. So basically you have to find resistance as well as capacitance. Okay, now here I know the impedance is given as this much, and there's a resistor and a capacitor. I don't have to draw the diagram also. I know that they would be at a phase difference of pi by 2, and the impedance, which is R times of root over 1.25, square of that would be equal to R square, the resistance square, plus the the capacitive reactance square, that is XC square, right? So this becomes what? R times of 1.25 is equal to, R square plus XC whole square. That gives you XC square equal to 0.25 R square, or XC equal to 0.5 times R. So we found out XC, 0.5 times R. But I need C, I don't want XC. Okay, so what's the relation between C and XC? XC is equal to 1 by omega C. Do I know the value of omega? I know value of omega in SI units, that's 500. So C would be equal to 1 by omega times of XC, which is equal to 1 by 500 times of 0.5 R, which is equal to, what will this be? 250, 1 by 250 R. Okay, this is the value of C, 1 by 250 R. Now I have to find the value of RC, that is the product of R and C. So R is R and C is 1 by 250 times of R. So that becomes what? 1 by 250. That will be what? That will be 4 into 10 to the power of minus 3. What's the unit of time constant? Seconds. Okay, R and C has a, when you multiply them, the unit is of time. So 4 into 10 to the power of minus 3 seconds. And the question says to find it in milliseconds. That's clearly 4 milliseconds. So in this problem, we are given a transformer which has secondary to primary turns ratio as 1:20. That means for every 1 turn in the secondary coil, there are 20 turns in the primary coil. And the primary voltage is given as 240 volts. The secondary voltage is not given to us, but there is a resistance which is connected to the secondary, which is 6 ohms. That is given to us. And we have to find the current that flows through the primary. Now I know the EMF in primary, but I don't know the resistance in primary, right? I know the resistance in secondary, but I don't know what is the EMF going on in the secondary. So how would I do this? So, okay, I know that this is a 100% efficient system. So it means that power in the secondary must be equal to the power in the primary, or the other way around. So IP times VP, which is the power of the primary, must be equal to the power of the secondary, which is V or IS times VS. Okay, this is one thing I know. Now this is IP is what I have to find out. So IP I can write as equal to IS VS by VP. I know that the ratio of the EMFs of a transformer is the ratio of their number of turns, ratio of the EMF of the secondary and the primary, basically what I mean. So this VS by VP can be written as NS by NP. Okay, this is the important part. So IP is equal to IS times NS by NP, but I don't know what IS is. Alright, so what am I going to do? So I can write IS again in the form of, I can say it is VS by RS, okay, times NS by NP. Do I know VS? I don't know VS. Okay, so what am I going to do now? I can say that because I know VS by VP is equal to NS by NP, right? I can write this to be equal to, I'm just going to replace VS by NS by NP times VP from here. Okay, I'm taking this VP on this end. So this is what I'm replacing this quantity by. Then you have an RS sitting in the denominator, then you have another NS and an NP. Okay. What does this tell us? This tells us that IP, basically this, is equal to NS squared by NP squared times VP by RS. Okay. Do I know VP, the potential in primary? I know that. I know NS and I know NP. The ratio of NS by NP I know is 1 by 20. So 1 by 20 whole squared times VP is 240 divided by RS. The resistance in secondary is 6. Okay. So let me find this. What do I get? I'll get 1 by 20 square will be 400 times 240 by 6. So 6 would go 1, 2, 3, 4 times, right? So it will be 40. So that will become what? 0, 0 cancel. 4 is equal to 1 by 10 amperes, which is equal to 0.1 amps. Okay. So the current flowing in the primary is 0.1 amperes.
For more videos and live lectures on the JEE, click on the subscribe button now.